Hi guys, I'm just going to go rapid fire through a bunch of compound circuits, and you can just watch if you want. Let's just make up some numbers. Let's say this is 10 ohms. Let's say this is 5 ohms, 3 ohms, and 7 ohms. Let's keep it wacky. So these we're not going to be able to reason our way out proportionally. We're going to have to do some math. So let's say this is 24 volts. All right, if we color code this, so we know we've got that happening, and we know we've got this happening. So we don't know what the voltage drop is across these guys, but we do know that this is going to be sort of orange in this position, from here to there, and again to there. And then we've got this little bit in the middle here, which is going to be a little bit different in terms of what's going on. So I know I've got voltage dropping across the 10 ohm resistor, and then the same two voltage drops across these branches, but the voltage drop is split differently across each branch. So I'm just going to dive into this stuff. Let's go at it. So first things first, what do I know about the whole circuit? Well, I know the total voltage for the circuit is 24 volts. Tells me that right there. And that's about all I can do. So I'm just going to start representing this circuit differently. Let's say instead of this being a path that has two, I'm just going to say it's got one resistor here. We know this one's 7 ohms. That's still the same guy. But now these two are in series, so let's just go ahead and say that they are acting as 8 ohms together because they're in series. This is still 10 ohms. That's still 24 volts. All right, so I'm just going to keep going. Follow along if you want. 24 volts. This is 10 ohms. And now we've got to figure out, well, what do these guys act like together? I'm just going to put these together, those two in parallel. Well, we know that you're going to have 1 over the total resistance, 1 over 8 plus 1 over 7. So 1 over RT equals, just do the math, 1 divided by 8 is 0.127. 1 over 7 is 0.143. So we know 1 over the total resistance equals these two combined, which is going to be 0.270. Now that's what 1 over RT is, so we've got to flip that. RT equals 1 divided by 0.270. We have to flip that over, and RT equals 3.7 ohms. All right, so that just tells us that these two, an 8 and a 7, act together to be around 3.7 ohms total. So we can boil those down into this, 3.7 ohms. We know this guy's still 10 ohms. All right, so we're closer. We're getting somewhere. So let's reproduce this. Say it's 24 volts. It's going to now through one resistor that is 13.7 ohms. That's what we can do. We can take this first drawing, boil these guys down into that, boil these two guys down into that. What that allows us to do is this. We know the total voltage is 24 volts. We know the total resistance equals 13.7 ohms. Therefore, we can find the total current, which is going to be 24 volts, 13.7 ohms equals 24 divided by 13.7. I had a college ready calculator handy, and that's going to be 1.75-ish amps. So that means that 1.75 amps is taken off. Sorry, let's go back to the top one. 1.75 amps. Ooh, these choices will come flying out of here. 1.75 amps. Go through here, and then some's going to go through there. Some's going to go through there, and they're going to split back up and end up being 1.75 amps here as well. Okay, so now we can get back into some things. So let's keep moving on. Let's redraw this guy. So we've got remember, we had 10 ohms. We had these again. 5, 3, 7, 5, 3 ohms, 7 ohms. All right, and we know that the total voltage drop is 24, and we know here you've got a current going through this guy, this first resistor. Highlight him. Data there. We know the resistance here is 10 ohms. We don't know the voltage drop through it though, but we do know the current. Remember, we figured out up here that because the total resistance of the circuit is 13.7, everything combined properly is 13.7, it means the total resistance through the whole circuit is 1.75 amps. So that means at this point, we have a current which flows through this guy. We shouldn't call it resistance total, we should call it resistance 1. That's our first resistor, our second, our third, our fourth. Let's do it that way. So current through 1 is 1.75 amps. All right, so then that allows us to find out how much volts dropped across there, and it's going to be 10 times, it's going to be IR, and it's going to be 17.5 volts. So what that means is of these 24 volts that we started with, we lost 17.5 volts worth of push getting through this first resistor there. So what's left over on the other side? We know it's 24, 24, 24, 24. Well, if you subtract that 17.5, when you get to the other side, it is going to be 6.5 volts is what's left over. Now, because these guys are all connected, in this kind of weird orange phase here, that means it's all the same up here. 6.5 on the top, it's going to be 0 on the bottom here. So that's convenient for this guy, because if we go all the way to this side, we know that the voltage drop across it, resistor 4, is 6.5 volts. And we got that from here. Started at 24, lost 17.5 across this, left with 6.5. 6.5 and 17.5 adds up to the 24 we started with. So we know the voltage drop across this resistor is 6.5 volts. We know the resistor here is, we said it was 7 ohms. Therefore, we can find the current. Current through that one is going to be V over R. 6.5 divided by 7 equals 0.92 amps. That's what's flowing through this guy. Does that mean the same amount of current is flowing through here? No, because yes, they have the same push, the same voltage drop, they have different resistances, so you're not likely to see the same. So let's take a look at each one of these guys. We know that resistor 2, that's here, we know that the resistance 2 is 5 ohms. We know the current through it. Do we know the current through it? We don't. But we can find it because we know that the whole branch is going to act like 8 ohms, 5 and 3 together. So for the whole branch, let's just change this. The whole branch. So resistance for 2 and 3, that's the branch, is 8 ohms. The voltage drop across it for 2 and 3 is 6.5 volts. Therefore, the current through 2 and 3 is going to be 6.5 divided by 8 equals 0.81 amps. All right, so what that means is that of the 6.5 volts pushing through here, and remember we started with 1.75 amps that's coming this way, and then it's going to split. Some's going to go that way, some's going to go that way. We've already figured out that in this path it's going to be 0.92 amps. We figured that out right here. So then how much must be flowing over here? Well, you've got 1.75 minus 0.92. That's what these should add up to. We should be able to find that out over here. So, and it should end up being, 0.81. So what's 0.81 plus 0.92 equals, hey, look at that. It's pretty much 1.75. Now we lost a little bit in the rounding, but mathematically it all works out. So let's get a little bit more specific. We know then that resistor 2 has 5 ohms of resistance. Now we know the current through it. equals 0.81 amps. Therefore, the voltage through drop across 2 must be 5 times 0.81 equals 4.05 volts. Now you can do some subtraction then to figure out what's going on in the next one, because remember we have 6.5 volts. We're losing 4 of them here. Means this one should be right around 2.95 volts to get to the second one. So let's go R3 down the bottom. We know that the resistance for that 3 resistor is 3 ohms. We know the current through it is 0.81 amps. Remember, it's a series, so whatever current is going through this 5 ohm resistor has to also go through the 3 ohm resistor. So they have the same current, and therefore you can find the voltage drop across 3. And that's going to be those two multiplied. 3 times 0.81 equals 2.43. And that makes sense. If you add those things up, it comes out to where approximately it's supposed to be. All right, so there's one more example.